Yeah, so vocab, everybody. And then, oh yeah, I left it showing, didn't I? Yeah, you can fill it in. The base angles theorem says if two sides of a triangle are congruent, well, first of all, if two sides of a triangle are congruent, what kind of triangle is it? Isosceles. But if two sides of a triangle are congruent, then the angles opposite them are also congruent. Pretty cool. So a picture of this, you could draw yourself an isosceles triangle. Call it, I don't know, GOT. And if triangle GOT is isosceles, what else do you know? If you know that, what other things have to be the same? Opposite angles. What we mean by that is, do you guys see how OT is directly across from G? That angle is the same as the angle that's directly across from GO. Right there. Cool. Yeah, and this comes from the fact that angles in triangles are really closely related to side lengths. But the relationship is across from the triangle. If this angle gets bigger, guess what else gets bigger? This side gets bigger. If this angle is the same as this angle, then that means these sides must be the same. It's kind of interesting. Okay, so the converse of the base angles theorem is the same thing, just flipped. If two angles of a triangle are congruent, are congruent, comma, then the sides opposite them are also congruent. So it's the same thing, except you're starting out. You're starting out knowing the angles are the same. And then from there, you're realizing what? Which sides?
The opposite sides.
The opposite sides. So which sides are going to be congruent?
Two top ones.
DO
Yeah.
and
OG.
OG. Okay, so let's put this into action. Is everybody okay with that so far? In example 1, it says in triangle PQR, name two congruent angles. P and R. Angle P is congruent to angle R. And by the way, this is an isosceles triangle. The legs are OP and OR. The base angle, or the base is PR, segment PR, and the base angles are P and R. And then example 2, what do you think? Yeah, Sam?
Okay, so we have our two congruent sides, so that means x and z, they're congruent. And so it's a triangle, so that means 50 plus x plus z equals 180. Yeah, 180.
Yeah.
And then, so you take 180 minus 50, you get 130, divide that by 2, then you get 65, and x is 65 and z is 65.
Okay, I like it. Are you guys cool with that?
Yep.
Sweet. Yep. And how many of you had to pause for a second and think, what do all the triangles add up to? All the angles add up to? Did you guys remember that it's 180?
I remember.
You remember that? Do you remember tearing the angles off of triangles?
Mm-hmm.
No, we did that in class. Some of you did. Okay. Well, if we want to show some work, I believe Sammy said subtract 50 from 180 and then basically divide it by 2, right?
Yeah.
Cool. Okay. There's a corollary to the base angles theorem.
Oh my god.
Fun.
Now, here's the thing. Postulates are statements that are accepted without proof. It's supposed to be kind of the fundamental building blocks. Theorems come from what?
Postulate.
Basically postulates. You take those things that you know and then you can prove relationship. Theorems have to be proven. And then next up is if you can make some new information directly from a theorem, it's called a corollary to the theorem. So there's like a system for naming these things. Does that kind of make sense? So a corollary is going to say, if the corollary to the base angles theorem says if a triangle is equilateral, then the triangle is also what?
Equilateral.
It's already equilateral?
Equiangular.
Equiangular. My spacing got a little weird in there. I think I put an I in there that doesn't belong.
Yeah.
I think so. I don't know.
I think you're just looking at the eyes in this.
You just throw me off. I don't know. I think it is right. Okay. What kind of triangle is equilateral and equiangular?
Regular.
Oh, sorry, it's just an equilateral triangle of both, isn't it? So all the angles are the same, all the sides are the same. We actually saw one of those in one of our previous notes recently, didn't we? Okay, what do you guys suppose the converse of this would say?
If a triangle is equiangular, then it's equilateral.
Triangle is equiangular, then we'll say it is equilateral. I kind of feel we knew this already, but here it is in black and white. Red and white. Well, let's put this all together. And by the way, I think this kind of makes sense. If two sides are the same, then two angles are the same. Well, if three sides are the same, doesn't it make sense that all the angles would be the same? I think it kind of makes sense. Take a look at example 3. What do you guys think? You want to take a stab at it, Ocean?
Sure.
Yeah.
Since those two angles are the right triangle, it's not a right triangle, it's just the triangle on the right.
Oh, like this one?
Yes.
Okay.
Since they're the same, then the legs will be the same.
So these two would be the same?
Yeah.
Oh, okay. Like that?
Uh-huh. And since the other triangle is equiangular, then it's equilateral, so then those are all also the same.
Oh, okay.
So
So what's x equal to?
x equals 7.
6. I don't know.
Well, I'm looking at my tick marks, and if that's 7, what's x?
7.
7.
And then y
So
would be
big Y.
3.
And oh, okay, yeah. And then y plus 4 is going to be equal to what?
7.
7 as well, right? But then we got to solve for y. What's y equal to? 3. It's kind of like a puzzle, isn't it?
It's fun to do puzzles.
Sometimes you're right. I agree. Example 4 is a little bit interesting. It says AC and segment AC and segment BD are each 14 feet long. Now, what's tricky about that is AC and BD have what point in between them? E. And sometimes people mistakenly think that E has to be a midpoint, and they're gonna write 7 and 7 here. Is there anything that's telling us it's in the middle of them?
Really?
No, but what we know for sure, and I could like redraw these, but I don't think I wanna. It's Friday, I don't wanna do anything extra, so. I'm gonna do like a brackety thing, kind of a brackety thing, and say that it's 14. And I'm also gonna do a similar brackety thing right there, and have that 14 there. Are you guys cool with that?
Sure.
Now, we're also told from the picture that CD is congruent to BA, isn't it? Because it's 8 and 8. Well, what the heck do they want us to do with this? It says, what congruence postulate can you use to prove that triangle ABC is congruent to triangle DCB? Write down what you think it is, and I'll come around and check. It's telling us that those triangles are congruent. We just got to find out why. And it's going to be one of those reasons that we've studied, right? Side, 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 angle, side, hypotenuse, leg, angle, side, angle, 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 side. Well, it's not the way I saw it. You may be seeing a relationship that could be proven, but it might take multiple steps to get there. But there's one way that's the most efficient way of showing that the triangles are congruent, okay? Why are those triangles congruent? So, it might, like in the long run, if you really spend a lot of time proving a bunch of stuff, but this might get you there, but I don't think it's the best way to go about it. Okay? Yes, sir.
Just for make sure I'm right back here, so.
Yeah.
Absolutely with these two, here's the city, here's the one right here.
Did you do what now?
But I have to do with these two, I'm not sure if it's the same, which one's it?
No, I think it just has to do with the line thing.
Alright, so I was-
I don't think you're gonna worry about the angle. But I think you're on track to that whole line thing. The line thing, I like it. Okay, so, ladies and gentlemen, check this out. So far, what do you know? What sides do you know something about for ABC?
They both share CD.
Let's see. They both share what?
Line CB.
Oh, okay. So you're jumping ahead for me. So far, we know this is 14 and this is 8.
Oh, yeah.
So we got side, right? On the other one, don't we have 14 and 8 as well? But then what's Aiden noticing? Don't they both share segment CB?
Yes.
And do we know if CB is congruent to itself?
Yeah.
We sure do. So at that point, we can prove these triangles are congruent by what?
Side.
Side. Side. Now, ladies and gentlemen, there are like a bunch of vertical angles in here, but none of those are gonna give you angles that you know for sure that are on the triangle, okay? The quickest way to do this is side. Then from there it says, explain why triangle BEC is congruent, or I'm sorry, is isosceles. Explain why triangle BEC is isosceles. What you got, Ocean?
2 of the sides or the legs are congruent. B, E, and C, E.
B and C are congruent? How do you know that?
Because they're at the same point on E. If the other 2 were congruent, then.
I mean, I think you are probably right,
Wait,
but
wait,
I
wait,
don't
wait,
know
wait,
how you know that exactly. What's that?
We don't have a way of proving that E is right in between.
Yeah, I mean, this could still feasibly be wonky somehow. I mean, it kind of seems like it has to be symmetric, but I haven't proved that this has to be a symmetric shape. So let's go with stuff that we have proved, that we have shown is possible. What was our last section of notes about?
Excellent question.
Using congruent triangles, CPCTC, right?
Yes.
Yeah, CPCTC. Let's think about this for a second. If these triangles are congruent, doesn't every angle have a congruent angle?
So I was on to something with that then.
For this maybe.
That's what I'm saying.
Oh, okay. All right, sounds good.
No.
There you go.
Probably no, Sam, honestly.
I don't know, we'll see.
I'm
So
saying you're on something like that first.
here's what I want you to notice. See these angles right here that are on this triangle? Oh, okay. It's just we were.
Yeah.
Okay. Oh, that's good. Do you guys see how this angle is an angle on the big triangle? And this angle is an angle on the other big triangle? Take a look at C and B. What do we know about them?
Congruent.
They're in the same spot, so they're congruent. You know this angle is the same as that angle. So I'm gonna say that angle, let me name this correctly, ECB, are you guys okay with that? Angle ECB is congruent to angle EBC by Y. CPCTC. By CPCTC. Now why is that helpful? Because now we know if these angles are the same, we can use the converse of the base angles theorem to say which sides are the same. You guys see we're talking about BEC?
Yes.
You guys see how we have base angles the same? So which 2 sides have to be the same? The 2 of them that are across. There and there. Now have we shown that it's an isosceles triangle? Why, yes. Yes, we have. All right, so segment CE is congruent to segment EB by the, technically it's the base angles converse theorem. But if you just say base angles theorem, you are A-okay in my book. What do you guys think? It's Friday. Yeah.
Thank God.
Well, ladies and gentlemen, hopefully that clicked at the end there. I honestly can't tell. Half of you seem asleep. So, but page 267 is some practice on this. And I would like for you to do this before I see you again on Tuesday. And I feel like that's important. You know why? Because you're probably going to forget it if you don't revisit it. I mean, I'm going to be honest with you. We're not going to quiz on this until probably on Tuesday. Probably on Wednesday we'll quiz over this. That's a long time from now, isn't it? So please practice a little bit. What's that?
I would sleep since then.
Yeah.
So
yes.
4.8 will
Hopefully
be
a few
Tuesday.
times. What's that?
So 4.8 will be Tuesday.
4.8 will be Tuesday.
All right.
Yep. And then Wednesday, we're going to do some quizzing, and then we'll start thinking about a test. But we won't have a test next week because there just won't be enough time.
Don't forget to